Now let us look at how we can combine this transistor, this two type of transistor, PMOS, NMOS, to implement logic functionality. Okay, so as long as we can build up logic functionality like AND or NOT, or like NAND nor not, like those functionality, if we can implement with this using the transistors, then we are actually one step ahead to build our processor and computing system, right? So let's see if it is possible or not. Now let's one configuration, simple inverter gate, which is a NOT, okay, which is a NOT. So what we do, we connect two transistor, one PMOS and one NMOS, drain to drain connection, and source connected to VDD, some power source, and source of the NMOS is connected to ground. All right, and our input, let's say X, is coming and connected to both of the gate terminal of this transistor. So this is a stack configuration. We are stacking up one PMOS and one NMOS, and my output is drawn from the junction of the drain connections of these two transistors. That is my output, and usually that output is represented as some capacitive load. So that's why I have given an capacitance there. A capacitance is this device which store some charges. If some potential is applied between these two terminal, some charge is applied, and if that potential is gone, this charge gets discharged. Like if there is a path to get the charge discharged, it will just discharge that electrical charge and just become an empty. So you can think of a capacitance device as a storage tank, which if potential is applied, electrical potential is applied, this charge starts filling up, and it just gets full and stays there till you kind of turn on a tap, which can drain. We call it a drain the charge. Which can basically like empty up the charge from this device. If somehow the connection to ground can be established, the charges like get away. We call it that phenomenon is called a discharging a capacitance, as long as it is connected to a ground. So now how this works then. Let's look at that. Let's say I am applying a logic 0 on this X, means your NMOS is off and PMOS is on. That means there is a current. We can imagine a current is established because this is on, but since this gate is off, that current won't be going to the ground directly, right? It is basically going on to this line, and since the current is established, there is some potential difference between this point of the capacitor and this point. So your capacitance get charged up. Okay, capacitor get charged up. So once it is fully charged, then what happens? This electrical line stays at a high voltage, like it is a voltage on state, right? And which is logical 1. Okay, so as soon as we are applying a 0 on this circuit, okay, we see the capacitance get charged. It stores all the charge coming up from the VDD side and keeping this line at logic high state, means a voltage on, right? Because this guy's capacitance is filled up. Now if I make a 0, then what happens? 1 on the input side. That means it turns off the PMOS but turn on the NMOS. So in that state, what will happen if there is a charge inside the capacitance? That charge has a path to get discharged to the ground, right? This has the capacitance, all the charges, and charges goes to the ground through the NMOS. So as long as charge is like all gone, as soon as it happens, this specific electrical line, that output, what we are calling it as an output, is at an logic state 0 because no voltage. There is no potential, no voltage on that line, so it becomes logically 0. Right? So that means we can establish a truth table. If there is a 0, a current comes in, charge up the capacitor, keeps this line at high state, logic high state, which is 1, logical 1. So 0, output is 1, and if we apply an 1 to this gate configuration, then there is a discharge path of the capacitance, and there is other path is closed, so no new fresh electrical charge can come into the capacitance. So what happens? You get a logic 0 at the output electrical line, because the charge is simply discharged, and it pushes the electrical state of that electrical line to a logic 0. So that becomes your logically an inverter, right? Logically an inverter, and we call it a logic. We draw it with a logic circuit symbol as this, right? A triangle and a bubble. So remember, like whenever we are drawing in a schematic like a symbol like this, underlying this diagram, there is this physical devices, one PMOS, one NMOS connected in a stack, and electrical connection is like this. Okay, so inside this one logic gate, we have two transistors connected in some certain configuration, so that it realizes, it implement the logic function of an inverter. With this same understanding, let's try to understand the NAND gate. Okay, NAND gate configuration is somewhat like this: two NMOS stacked on top of each other. Okay, and one is driven by, let's say, logic input B, another is driven by logic input A. Okay, and then the PMOS are in parallel with each other but stacked with this NMOS stack. Now why they are parallel? Okay, electrical study. Okay, why they are parallel? They have also certain relation between them about the sizes and so on and so forth, but for this class it doesn't matter. Okay, just take it as a granted. These two PMOS are in parallel and stacked over the NMOS stack, which is really serially connected on top of each other. And each of the PMOS gate is connected to A and B terminal. Now what happens to let's say I have a 1 here. Okay, so only if both of this logic of A and B is 1, these two NMOS is turned on and there is a discharge path from the capacitance to the ground, and only that configuration will make your Y or output as 0. Okay, so with this configuration 1 1, this two NMOS is on, this two PMOS is off, so no new charges can come up into this capacitor, so capacitor will fully discharge and you get a logic 0 as an output of that circuit. Okay, so that becomes your 1 1 0. So any other combination if you think of, then either one of them is closed, like not allowing any electron flow through it, any charge flow through it, or both of them are closed, like so then what happens? There is no path for capacitance charge to get discharged to the ground. So either this is closed or that is closed or both are closed in any other configuration other than 1 1. And other than 1 1 configuration, if you look at the PMOS, either one of them or both of them are open. That means they are ready, they are kind of charging this capacitance on any other configuration. So that gives you this truth table. Like any configuration other than 1 1, you get a 1 at the output because your discharge path is turned off and your charging path is on. Either one of them is on for your NAND, and it will charge this capacitance. So 0 0, both are on, your output is 1. 0 1, one of them is on, which is like this one is on, this one off, but still it gets charged, so it is 1. 1 and 0, so this guy is on, this guy is off, this guy is on, so that gets charged. So remember, like I think I just said it a little wrong on the 0 1 combination. So 0 for PMOS is on, right? So 0 1, this transistor would be on and this transistor would be off, but still this guy gets charged. 1 0, this transistor is off, this transistor is on, still this capacitance will get charged, your output will head to logical 1. Only 1 1, both the transistors are off, both these NMOS transistors are on, so it establishes a discharging path, capacitance gets discharged, and you get a logic 0. So this is the implementation of a NAND gate, which we can look at the symbol. Is a logic circuit symbol is like this. So whenever you see this symbol in your logic circuit diagram or any other logic circuit diagram, you can imagine under the hood there are like 4 transistors for one simple NAND gate. Okay, there are 4 transistors, 2 PMOS, 2 NMOS on this. Now continuing on the same notion, that NOR gate. NOR gate is just you can say a mirror image of the NAND gate, in the sense that here in this case your NMOS are connected in a parallel, then PMOS is connected in a stack configuration or with a serial. So PMOS serial connection stacked with NMOS parallel connection, and it works just the reverse way of the NAND gate. So only if both A and B are 0, both these two are off, so it does not, this capacitance does not have any discharge path. Not only that, this for 0 and 0, both of these guys is on, so there is a charging path established and it will charge up this capacitance. If let's say if this was empty beforehand, it will charge up and bring up the logic of the output of this circuit to a 1. So 0 0 is 1. So any other configuration, okay, what will happen, one of these PMOS will be turned off or both of them will be turned off, and one, that means there will be no path to charge this capacitance. Not only that, with any other configuration other than 0 0, we'll have either one of these NMOS on or both of them on. That means there is an established discharge path from the capacitance. The capacitance will happily discharge and bring down the logic level to 0. So from the upper side there is no charge coming, and additionally we are discharging, this capacitance gets discharged to one of the transistor or both of the transistor, depending on if it is 1 0 or 1 1 or 0 1. Depending on that, it will get discharged either through one of them or both of them. So that gives you a logic function of 0. So if we put them in a logically, 0 0 gives 1, 0 1 is 0, 1 0 is 0, 1 1 is 0. So that's a NOR, right? That's a NOR functionality. Is a Boolean function, and symbol is this of the NOR circuit. So then you can, if you look at any logic circuit, it has a NOR in it. You can well imagine under the hood it has again 4 transistors, 2 PMOS, 2 NMOS, and it has a very specific electrical connection between them. Okay, so this is our NOR gate. Now these 3 gates, NOT, NAND and NOR, are the fundamental logic gates. On the contrary, fundamental logic operation in the Boolean algebra, as you reviewed that in a couple of lectures back, is a NOT and OR. That's why logic functions are often converted into terms of complement of the basic Boolean operation, because you have more fundamental logic component you can build up is a inverse logic. You can build a NOT, you can build a NAND, you can build a NOR. Okay, so that's why it's your expressions are fundamentally turned into a NAND based expression or NOR based expression. Inverter is of course there, and that's why De Morgan rule is very important. De Morgan, that theorem or that rule enables you to convert one positive logic into the negative logic. Okay, so that's why this De Morgan has a very special application in digital logic design. Now, fundamental logic gates, using them we can definitely implement an AND. We just combine one NAND, one inverter, that becomes your logically AND. OR implementation similar, one NOR, one inversion, it becomes an OR. Of course, we can have an alternate OR implementation as well. If we try to apply De Morgan is like something like this. If we do an inversion of A, inversion of B whole invert, means like your primary input is get inverted and going through a NAND gate, it becomes OR. So you can either use a NOR followed by an inverter, becomes an OR you can use a De Morgan rule to apply a NAND gate and inverter gate in a certain way to make an OR. All right. So and you can use also, like you can actually compute the transistor count in them. Like this guy has 2 transistor, this guy has 4, so it becomes like 6 transistor. This one has a 4 transistor, this is 2, this is 2. So it basically, this implementation an 8 transistor, right? So maybe this implementation is a little more efficient than this one. But if you need to have, like let's say you don't have a NOR gate in your hand, you need to apply a NAND gate, you can apply that and make a OR functionality. Okay. Some more logic gates, you can start combining them, like a XOR gate, like which basically X Y bar or X bar Y. So we have all this all the logics, like we have just built up an AND, we have built up and inversions, we have built up an OR. So we can combine those gates and make a XOR. Similarly, XOR we can make from a logic function. Just to note, in real life, XOR, XNOR are not usually built up connecting the other logic gates, other more fundamental logic gates. XOR has a very, very custom designs, and this is out of scope of this class. But this is made due to the fact we can make other type of transistor configuration and connections to make a faster XOR and XNOR. Why we are interested in this? Because fundamentally your addition circuit, we'll see later, that logical addition circuitry is mostly XOR gates. So we need to make it faster to make a faster addition operation. But for timing and for this class purpose, you can think of this whole thing is like a combination of different other more fundamental logic gates. It doesn't have any custom design associated with that. You can imagine it, but just for your information, no one builds XOR like combining basic logic gates. It has a very custom design around it, and every processor company thrives and try to make their XOR design as fast as possible. Okay, and they're all trade secrets, by the way. Anyway, there is another logic type called a buffer, which logically doesn't do anything. It's basically your logically is Z is X, whatever is logic your input, putting an input it is an output. The application of the buffer in the digital circuit is to strengthen the logic signals. Okay, so let's say if you are driving from a logic gate a very long distance another gate. Okay, in terms of microcircuitry, even like 1 micrometer distance is considered as a big distance. Okay, so let's say you are driving a far away gates, then what happens, since it is all electrically and it's a physical phenomena, your signals start get degrading, your logic high or logic low starts get degrading, and it may become also like inverted through the electrical things, right? So you can think of the buffer as an electrical amplifier, signal amplifier. It just picks up a like logic signal, amplifies, and makes sure it goes as the same logic into the next stage. So if usually two logic components, one driving another, sits far apart, we usually insert buffer to make sure your logic value transfer is good enough for the target device. Okay. There is one more component, is called, we call it a tri-state buffer, which is a very special type of buffer, which is needed for the electrical isolation from one circuit to another. Okay, so how it works: if E is logically 1, then you transfer it, this whole thing act normally like a buffer. You put a 0, you get a 0, you put a 1, you get a 1, as long as your E stays to 1. Now if E becomes 0, then whatever logic at the input side doesn't matter, your Z output becomes electrically isolated output, like high Z. Okay, it is electrically detached from the rest of the circuit. There are applications of such gates, especially in the memory, bidirectional data path design, and we'll be seeing actually in this specific application of the tri-state buffer conceptually during project 2, and physically when we implement things with the gate level, physically we'll see in the project 3. Okay, we need to use the tri-state buffer there to make an in-out kind of port out of this memory, okay, or any other digital component which actually supports in-out type of IO direction. We need to use a tri-state buffer like this one.